Welcome to Scale Up University. Welcome to Probability for Machine Learning course. So this is the lecture 5 of module 2, Source of Uncertainty 3, that is imperfect models. So in this lecture, we will be discussing about the third source of uncertainty, and that is imperfect models. Imperfect models, they cause uncertainty. So like whenever model perform poorly, like let us suppose you trained a model and you are getting like a very poor model performance in the lab, then definitely the reaction, the instinctive reaction would be either we will be needing more data, the poor performance is because of the lack of training data, or we would be needing a bigger model, a more complex model. And many a times it has been seen that okay, you trained a model in the lab, you are not getting a good, your model is not performing good. And what is the meaning of poor performance? Let us suppose it is a classification model, it is classifying wrongly. Or if it is a model which is responsible for some sort of predictions, it is doing wrong predictions. So whenever the outcome is wrong, then we call it the performance is poor. So you trained a model and you saw that okay, the performance of the model is poor. And to enhance the performance, you are like supplying it more and more data, and you might also be like making it more complex. Like if it is a deep learning model, you might consider adding more and more layers. And many a times it has been seen that despite of all such efforts, like you are bringing in more and more samples, you are pre-processing the data, despite of all such efforts, no improvement in the performance it has been seen. And then you might get puzzled, why is it so? So the main reason for that, like one more very interesting and important factor which affects the model performance, is the imperfect model imperfection. And that is what we will discuss in some good detail. What do we mean by imperfect models? So model imperfection is one of like a very important factor which decides the model performance. So if the model is imperfect, then we will have unavoidable uncertainty. Meaning to say that if the model is imperfect, regardless of whatever data you supply, regardless of you pass millions of training samples, like which are like very well polished, like pre-processed, clean data, millions of clean data you pass as training, and regardless of you keep on increasing the layers of deep learning or complexity of the model will not perform. There will always be poor performance because of the model imperfection. So model imperfection means unavoidable uncertainty. And this lecture is all about that. In this lecture, we will discuss in some good detail about imperfect models. And this lecture will explain why imperfection creates uncertainty independent of data size or model scale. So model imperfection will create an unavoidable uncertainty that is totally independent of the data size and the complexity of the model or the scale of the model. So a very important discussion we will be making in this lecture, and you got a crux, that a basic understanding, like the idea that what exactly we will be dealing in this lecture. So if we look at the topics we will cover in this lecture, so first we will be discussing why models are approximations. No matter how complex model you make or what algorithm you use, models are always approximates. They cannot represent the true reality. And why is it so? The reason for that we will discuss. Then we will be discussing simplifying assumptions in machine learning models. In machine learning, whenever you are training a model, preparing a model, building a model, assumptions play a very important role. So that we will discuss. Then we will discuss something called as model bias. What is meant by this bias? That we will discuss model bias as a source of uncertainty. Then we will talk about why all models are wrong. And this is something very interesting, and you might be puzzled like, I am telling that all models are wrong. Like, no matter what model you take, you train it with billions of data, billions of training data, sample size, still it will be wrong. So, all models are wrong. So, it will be a very interesting discussion that we will be doing. Then we will be like looking at the difference between model error versus data uncertainty. It's a very important discussion we will be making. You should be like, it should be very clear to you the difference between model error is very different from data uncertainty. So that we will discuss. And then we will be discussing why better data does not fix bad models. That we just like we saw also, like if the model is imperfect, no matter millions of data like sample you take, a very clean data you take, the model will not perform. So better data does not fix bad models. And one more very interesting thing, better models don't fix bad data. So from these discussions, you will get a feel that, okay, in machine learning, both models, like we should aim for a good model and good data. If any one of them is bad, then it will affect the performance. So for a like a good performance machine learning model, we need both good model and good data. And then we will discuss interaction between model capacity and uncertainty. So this will be a very interesting discussion. And finally, we will be concluding this lecture with discussing diagnosing uncertainty, like how we can exactly diagnose uncertainty. Because uncertainty is something which is inherent in machine learning models. Because all machine learning models are wrong, they are not perfect, there is a scope of error, and hence uncertainty is something which will be there, and we should learn to handle uncertainty because we cannot avoid uncertainty. We have to handle uncertainty. So that is what we will discuss, how we can diagnose uncertainty. So all these topics we will discuss one by one. It would be a very interesting lecture. So straight away we'll start with the first lecture, first point of this lecture, first topic of this lecture. So this lecture is the module 2, that is uncertainty in machine learning, and this is a lecture 5, source of uncertainty 3, that is imperfect models. The first topic is why models are approximations. So models are always approximates. They cannot represent the true reality. So now the big question is, why is it so? So if we look into the reality, reality is the world where we live in. So the core reality, the world where we live in, it is a high dimensional space, meaning to say that it has got like lots and lots of features, mostly like the dependency of the target variable on features is non-linear. So the dependency is non-linear. Context plays a very important role. The real world is context dependent because the same scenario in a different context will behave differently. So context plays a very important role. And dynamic. The real world is dynamic means it is changing. Today's reality, tomorrow it might completely change. So whatever holds today, tomorrow it might not hold. So the real world is very dynamic. So the idea is that reality is infinite, complex, and ever changing. So these three things are very important about the real world. So the world where we live in, we are constantly generating data. The data is changing also because so the real world is infinite. Infinite means the data we are generating, the scenarios, the possibilities that is infinite. It is very complex, high dimensional, non-linear, context dependent, and it is ever changing, dynamic. Unfortunately, we cannot like make use of all these things. Like when you are training a model, you will always be end up taking a sample of reality, a subset of reality. So the models we will be building, the machine learning models we will be building, it will always be containing a sample of reality. The training data will be finite. Real world data might be infinite, but we cannot train a model using infinite. So the training data will be finite. It will be structured. because it cannot take into consideration all the features, it cannot take into consideration all the non-linearity, it cannot take into consideration all the context. So that's why, and it is constraint plays a very important role, because when you are training a model, that the data is finite, the model is very structured, and constraint, it is constrained, many constraint we take into consideration, and hence we eliminate many features, we eliminate many non-linearities, we eliminate many context. And because of all this, it's very clear that okay, model represents a subset of reality, a part of reality. Model cannot represent true reality, and hence the result given by the model will be approximate. Since model is not representing the true reality, the result of the model has to be approximate. So approximation is not a flaw. Approximation is not something like we are lazy, or we don't have computing power. It is something which is inherent, which is a necessity, because we can never like make use of all the things, all the scenarios we cannot consider while training a machine learning model. We have to do some sampling for the data. We have to introduce some sort of structuring constraints, and hence the result of the model has to be approximate. So approximation is a necessity when it comes to training machine learning models. Now if we look at one example, like house price prediction. So in real world, if you look at house price, so house price, it depends on many factors, like location plays a very important role in deciding the house price. Negotiation behavior plays a very important role, because if somebody is very good in negotiation, the house price will get affected. Market psychology and legal nuances. So all these things and many more factors comes into picture, which influences the house price. But unfortunately, when you are training a machine learning model for house price prediction, you will not consider all these scenarios. You will not consider all these possibilities. You will not consider all the factors, all the features which will influence the house price. Rather, you will take a subset of it. So that is the constraint you will introduce, some sort of structuring and constraint. So you might consider the area, you might consider the number of rooms, and you might consider price history in deciding the house price, in predicting the house price. So since we are taking like a subset of reality, a part of reality, because we know that okay, house price, it depends on so many factors, but while training the model we are taking only few of the factors, or we cannot take all the factors, because so many factors might be there. So that's the reason. And because of that, the price predicted will not be accurate. It will be approximate. And now it's making sense that, and hence we say that like all the machine learning models are always approximations, because whatever discussion we are making, it is applicable for all AI models, like all machine learning models, all deep learning models. This discussion is applicable. So very important takeaway, key takeaway is that the model, it compresses reality. That is very true, because we know that okay, model cannot capture the entire reality, it has to compress the reality, and hence uncertainty is the compression error. Because the model is compressing the reality, it is like unaware of some reality, and hence it is not trained perfectly. There are certain patterns which it is unaware of, and when those patterns are given as test input, model will make error. It will make mistakes in doing predictions, and hence that compression error is causing the uncertainty. And what is uncertainty? Uncertainty means we can, like whatever output the model is generating, we cannot say that it is correct, we say that it can be correct. So that is uncertainty. Okay, now we look into the next topic of this lecture, that is simplifying assumptions in machine learning models. So now see, assumptions plays a very important role in machine learning. Why? Because see, models, they must assume, like which variables matter. Because see, we already saw that here variables are like features. So last slide we saw that house price prediction, house price, it depends on so many factors, so many features, so many variables. Now we cannot consider all the variables, so we have to choose, okay, which variables we should choose. So we have to make assumptions. We make an assumption that okay, 100 features are there. Out of those 100 features, we make an assumption that okay, these 20 features might not be that much influential in deciding the house price, and our assumptions might be wrong also. What if so assumption is something which we have to make. Like whether you are making a ML model or a deep learning model, you have to make assumptions, because you have to choose. So you have to choose, you have to assume that okay, which variables matter and how variables interact. Like it will be a linear, non-linear relationship, and what relationships look like linear models, non-linear models, all that. So assumption is something which we have to do. That's why we are calling that assumptions are necessary. And assumptions only make learning possible, because with assumptions we are reducing the complexity of the problem. Otherwise, if you don't do assumptions, then let us suppose the target variable, that is the house price, it might depend on thousands of features. Then you will end up including thousands of features, and like it will be very hectic actually. So assumptions make learning possible, but wrong assumptions, it create uncertainty. Wrong assumptions create uncertainty. That also makes sense, because see, if you are making wrong assumptions, then the output will be wrong na. And if the output is wrong, then how can we very sure about the output? Like whatever the machine learning model, the output is generating, it can be correct also, it can be wrong also. So uncertainty will be there. So wrong assumptions, they create uncertainty. Okay, now let us look at one real example, real world example of this. So uh, let us suppose we have to like deal with the uh, sales versus advertising trend. Like we are assuming that okay, because we are assuming that okay, it makes sense that okay, if I keep on increasing the advertising spend, or if I keep on increasing the advertising activities, sales will increase. It makes sense also. It's like very like a common sense that okay, common sense says that okay, if I just do lots and lots of advertising, the sales will increase. But if for this trend, if I make an assumption that okay, this trend will be a linear thing, the if I assume that okay, the relationship between the advertising and sales is a linear straight line relationship, then what will happen is that the machine learning model I will make will be a straight line. So this straight line is the machine learning model. Now what will happen is that these points are actual reality. Like the point I am making in this green color, uh, these are the reality. But the point on the line which the ML model will predict. So I'll tell you how to interpret this graph. So let us suppose advertising spend is somewhere here. I'll use a different color for that. Okay, let me use a white color. So okay. So let me first clear everything. Okay. So just look at that white cross mark. So as you can see here, white cross mark, which I'm drawing. So let us suppose that is the advertising spend. Now I want to make a prediction that okay, if my advertising spend is this, then what will be my sales? Now the point on the line, which is like a circle, I will mark it with a red point. This is what our model will predict. But the just above this point, which I am marking with green, the point which I am marking with green, what it is? It is the actual sales. So red point is the sales predicted by our machine learning model, and the green point is the actual sales. So definitely the sales which our machine learning model is predicting is relatively low. So here what we are doing is that we are underestimating. So the idea is that the prediction is not accurate, it's not correct, because we are predicting low sales, but in reality for that particular spend the sales will be high. So this assumption which we made, straight line assumption, it introduced this uncertainty, because it is a wrong assumption we've made, and because of that we can see a error, this uncertainty we introduced. And reality shows that the relationship between sales and advertising is basically a non-linear, like this graph, you see now, this non-linear graph. So that is the reality. So reality shows that okay, uh, with spend, with advertising spend, the sales will increase initially, but after a point of time it will start getting saturated, because people then will get like irritated using seeing the same ad again and again. And many other factors might be influencing the sales. So the ML insight which we should take away is that assumptions are something which is very necessary, we cannot avoid it, and assumptions defined the shape of uncertainty. So this is very important discussion we are making. The assumptions we make, it will define the shape of uncertainty. If you are making lots and lots of wrong assumptions, then uncertainty will just amplify. So see, assumption is something which we have to make, and we have to be very smart enough in making the right assumptions. And that is why machine learning or artificial intelligence is an art, because here, like this guess you are making, here intuition and many other factors will play a role. Okay, now we'll look into the next topic of this lecture, that is model bias as a source of uncertainty. Now, so before discussing model bias as a source of uncertainty, let's try to first understand what is the meaning of bias, like model bias. So see, what is the meaning of bias? Bias means we are, it's like a sort of partiality, like we are inclined more towards something, or we are giving more importance to something. So we are going to bias. We say that okay, opinion should be unbiased. Opinion should be unbiased means regardless of the two parties, whatever you are selecting, or your selection should be unbiased. So it should be based on true factors. And biased opinion means okay, you are giving an opinion which is more favoring a particular side. So that is the meaning of bias. And model bias means when you're training the model, you are basically uh, giving more preference to certain features. Like you feel like okay, these features are influencing the target, or by default, like when you're training the model, some features they might get more preference, and hence we say that we introduce the bias. So very important discussion we are making. So model bias arises when the model class cannot represent the true relationship, and this is very clear that okay, whenever the bias is introduced, then the end output will be different. It might be wrong. So bias is systematic error, it is not randomness. So bias is something which system introduces. It's an error, because see why it's an error, because whenever the bias is introduced, the model will like give wrong answers. It's an error, and it's a systematic error because it is not an something inherent. This is something which we introduce, or the system introduces. And how we introduce is that we know that in machine learning, assumption is something which we have to do. We cannot avoid assumption, we cannot skip assumption we have to do. So when you're assuming, what if you're doing a wrong assumption, then that wrong assumption might introduce a bias, because like here in the previous example you were telling that okay, linear relationship, that the relationship between the advertising spend and the sales is a linear relationship. So you introduce a bias, you're favoring linear relationship, you're giving more importance to linear relationship, but in true reality it was non-linear relationship. So you introduce the bias with a wrong assumption. So bias is something which we introduce, it's a systematic error, it's not something inherent or something random. So it's systematic error, not randomness. So let us get some more feel about the bias with a very interesting and a real example. So if we do spam detection with few features, so let us suppose spam detection. What is spam detection? Like in the email, the spam detector will detect whether the email is a spam or not. So if we are only considering few features, like let us suppose we got an email, like the email says that it's an urgent mail and you want a price. And then for spam detection, we are using a very basic model and just considering few features like keyword count. We are just taking into consideration keyword count. So here two keywords are there, which is related to spam, that is urgent and price. So the keyword count is 2. So the keyword count is very less actually. So we will classify this email as not spam. So here what we did, we trained a machine learning model and we took only few features, only one feature we took, that is keyword count. And based on that, we predicted that okay, the given mail is not a spam, but in reality it is a spam because you want a price, it's a spam email. But in reality, for detecting spam is not just dependent on keyword count, but many other factors, many other features decide whether the email is spam or not, like the context, the intent, the semantics. And we missed all this. So ideally, the what should be there is that okay, urgent is there, and you want a price. This is the email. Then this urgent is like see. Urgent is a contextual word because in certain scenario urgent can lead to spam, and in certain other scenario urgent can lead to a non-spam email, because in non-spam email also urgent can contain, but in many spam email urgent might be there. So context will play a role. And here wanna price and all that, the intent is wanna price, and with that urgent is associated, then very easily we can say that it's a phishing attempt. So the intent is, so I'm just giving an idea that okay, for the true spam detector, these features we should consider, but we took only few features, and because of that we introduced bias. So now it's very clear to us that okay, how we can introduce a bias in the model by taking few features. So and now it's making sense. Very important point I'm making is that even with infinite data, the model fails. So this is something very interesting. Like, see, if there is a bias in the model, it means model is inclined towards certain features. Only few features we are considering, and those features might not influence the target to a great extent. There are many features we've missed, and hence we introduce the bias. And when there is a bias in the model, no matter what data you supply, infinite data you supply, very clean data you training data you supply, the model will end up giving wrong answers. So even with infinite data, the model fails. So this bias is very dangerous. And now I think you're getting a feel of it. So bias limits what a model can ever learn, because when you're taking few features, because you're assuming that only okay, the house price depends only on these features. So that's the assumption you made. And if that assumption is wrong, because there are certain very important features on which the house price depends, if you miss those features, then you introduce the very big bias in the model. And no matter infinite data you supply, it's gone. So these are like very tricky things and very like a sharp discussion we are making, which will like optimize your machine learning model, because if you take care of all these things, you will be able to optimize the performance of your machine learning model. Okay, now we will look into the next topic of this lecture, that is underfitting versus overfitting. Okay, so these two are very important concepts, underfitting and overfitting. You might have come across this many times. So let us understand it very carefully. So first let us understand what is underfitting. Underfitting means when the model is too simple. And what is model is too simple means we are taking very few patterns, a few features. We are taking very few features. When you take only like few features, then the model will be too simple. That is one like scenario. Other scenario is that if you are training a deep learning model. So see, one very interesting discussion, I'll make it here itself for your better understanding. In machine learning, feature engineering we have to do. We have to decide, okay, which features we should choose. But in deep learning, feature engineering is done by the model itself. You are not at all concerned in shortlisting the features. You just supply everything. Deep learning model will on its own identify important features and it will train accordingly. So in machine learning context, if you are like assuming only few features, then underfitting will be there. But in deep learning, if you are taking few layers, like you are not using many layers, the model is very simple, then underfitting will be there. So underfitting means model is too simple, and model is too simple means either few features or few layers, you will miss patterns. So underfitting will always lead to missing pattern, means many patterns the model will not learn, and ultimately there will be very high bias. Model too simple implies very high bias. So very important discussion. It's making sense also because only few features we are taking, so the model is biased towards those features. In reality, there might be many more features which might influence the target. We are completely missing it. So we are biased towards few features. So underfitting always introduces high bias. Underfitting, many patterns we miss. Machine learning model, deep learning model, it misses many patterns, and hence very high uncertainty will be there. If we talk about overfitting, what is overfitting? Overfitting means model too complex. Model too complex means now you are taking lots of features. You are taking lots of features. You are taking unnecessary features as well. Like overfitting means uh, you are taking those features as well which might not influence the model at all, the target variable at all. So model is too complex. We are taking lots many features, or we are adding unnecessary layers in deep learning. So when model is too complex, what will happen is it will it will start learning noise. It will start learning noise, and because of that there will be high variance. So here there will be no bias, because see, in overfitting there is no chance of bias because we are giving equal weightage to all the features. We are considering all the features, so no point of bias in overfitting. But the problem is that in overfitting, since we are taking unnecessary features also into consideration, that might introduce unnecessary noise. So the model, it might start learning noise. So unnecessary features is something which we call it as noise. So the model, it will take into consideration unnecessary features which has nothing to do with the target variable, and we will start just learning that. I'll give you an example. Like in predicting house price, the name of the customer who, like in the historic data, let us suppose I have the name of the customer who already purchased some property. Now that name has nothing to do with the house price, and if I include that name also in training my machine learning model, it will introduce noise. So model too complex, high variance, and that will also lead to uncertainty. So both will create uncertainty. Underfitting and overfitting both will create uncertainty, and the goal is to maintain a balance. So if we look at a real world example, like a machine learning a specific example, polynomial regression. So in a polynomial regression, if you take degree 1, then definitely it underfits, and if you take degree 10, it will overfit, and neither generalizes well. So the moral of the story is that more complexity does not mean less uncertainty. So here one very important myth I am like clearing it, a very important confusion. Like there is a belief in like machine learning practitioners that okay, if I just keep on increasing the complexity of my model, I will achieve state of the art accuracy. But unfortunately, it is wrong. So more complexity does not mean uncertainty, because if you keep on increasing the complexity of the model, you might be introducing unnecessary noise. You might be introducing the features which have nothing to do with the target. So overfitting. Okay, now we'll look into the next important topic of this lecture, that is why all models are wrong. Now see, now it is very clear. Like if you just think about all the discussions we made in this lecture, we started by saying that okay, approximation is something which is inherent, because machine learning models, when you're building machine learning models, you cannot capture the reality, because the reality is something which is infinite, which is very complex. But when we are training the model, we are taking a finite sample of reality, a subset of reality. We are introducing some sort of structure, some sort of constraints we are taking into consideration. Because of that, the output of the model has to be approximate. Uncertainty is something which we cannot avoid. Uncertainty will be there, and hence all models are wrong. And the meaning of this is that models can give wrong answer. Models can give wrong answer. If the models can give wrong answer, I can say that models are wrong. It does not mean that every time it will be wrong, but it means that the probability of giving it the perfect answer is very very negligible. Like if I am doing a prediction, I want to predict a price. If the real price is 300, actual price, it is very difficult that our model will predict exactly 300. It might predict 299, 299.99, 300.01. So approximate. Since models are approximations, we cannot expect it to give the perfect answer, the exact correct answer, and hence we say that all models are wrong. So see, all models are wrong. This is exact thing, but some are useful. And despite models are wrong, we can make use of it, because with approximation, we will get something close to the reality, and that is also sufficient for us. With that also we can like have some very interesting real world applications. So models are wrong because reality is richer than equations. Context changes. Simplification distort truth, because we introduce we make things simple, so it distort truth. And usefulness comes from managing error. So uncertainty is something which is inherent. Approximation will introduce uncertainty, and if we can manage that uncertainty using probability, then we can make use of that uncertainty, we can make use of that approximation. And the best example of that is classification, because in classification there is a threshold that okay, if I am getting anything below that threshold, that number, like that number is like, let us suppose 0.3 is the threshold. So if I am getting anything below 0.3, I will classify it as class A, otherwise I will classify it as class B. So this is called as managing error, because now definitely whatever output the machine learning model it is producing, it's an approximate, it is not the true value, and it is having error. But we are making sense of that error by telling that okay, 0.3 is the threshold, anything below that is classified as class A, anything above that is classified as class B, and this will give you a very good result. So this is one way of managing error, and in machine learning models you will see so many different ways. So if we can manage errors, if we can quantify uncertainty, and if we can make better decisions than guessing, like if we make educated guesses or scientific decisions, if we make based on some scientific principles or some techniques rather than just making a blind guess, if we can do all this, then definitely we can make use of these models which end up giving wrong answers. We can make use of the approximation, and that is what is machine learning is all about. Machine learning is all about making the models useful, despite the models are giving wrong answers, despite the models are giving approximations. Machine learning, we will discuss so many techniques wherein we will make models useful. we can make apply it in solving some real world problems. So one example is weather forecast models. So if you talk about weather forecasting means doing some predictions about the weather. Okay, tomorrow it will rain, or it will be a sunny day, something of that sort. So even advanced models, they produce probabilistic models, forecast. So forecasting is all about probabilistic in nature, that okay, 60% chance is that tomorrow it will rain. Now, since it is not giving us the true reality, it is giving us an approximation, and probability is something which might go completely wrong also. So let us suppose the model is predicting that 80% chance is there, 80% chance is there that tomorrow it will rain, and it might happen that tomorrow it will not rain at all. It might happen. So probability, it might go wrong also, but still it makes sense to us, because it will fail only beyond a horizon, and yet they are invaluable. Yet we make use of forecasting, because we know that forecasting might end up wrong, because it's a forecasting that okay, tomorrow 80% chance it will rain, and it might happen tomorrow it will not rain. But what if it rains? Then we can alert the farmers, or we can alert some uh, construction workers that okay, 80% chance is there tomorrow it will not rain. So if they are well prepared, sorry, 80% chance is there tomorrow it will rain. If they are well prepared, then if it rains, they might save something interesting, it might have some real value. And if it not rain, then they might uh, like incur some loss. So here, that is what managing error. And how we will manage error is that if we should not uh, announce tomorrow is holiday, like some construction work is going on, 80% chance is there tomorrow it will rain. So the smart decision, making better decision, what is making better decision is that okay, 80% chance is that tomorrow it will rain. So what you do, we will continue the construction activity, but with some measures in place, some safety in place, so that if it rains, we can just cover up ourselves, or cover up some sensitive areas where like concreting or something, like we want to protect it from rain, we can cover it up. And with that better decision, we are managing the error, because if it will not rain, then also we will not lose the productivity. It will be a normal day wherein workers will end up working. And if it rains also, then we are creating value, because now the construction workers are well prepared. They will just manage the rain. So we created value. So that is what is AI is all about. In AI can make mistakes. Machine learning, deep learning, it can make mistakes. So when you're designing a solution out of it, it has to be very smart in that way that you have to manage error. You have to keep in mind that if it make wrong predictions, it should not be harmful. How I can, so that is like a risk management, how I can handle the risk. And if you are able to handle that risk smartly, then you can make use of the AI solution which you are building. So that's the main idea. Okay, now so the key takeaway is that wrong models can still be useful if uncertainty is acknowledged. So it's all about managing errors, making better decisions. In this way, we can acknowledge the uncertainty. Okay, now we'll look into the next topic of this lecture, that is model error versus data uncertainty. So see, first let us understand what is data uncertainty. So see, data uncertainty, it makes sense also. Like looking like what is data uncertainty means, some noise is there in the data. Data is uncertain. Data is uncertain means data might be wrong. So some noise might be there in the data. Some missing values might be there in the data. Some label errors might be there. The data is not perfectly cleaned. It might have some unnecessary stuff in it, like some missing values, some label errors, some noise, background noise, faulty sensors. That is data uncertainty. So now it's very clear that okay, the data we are using to train the model, if it has got uncertainty, that's a problem. And model uncertainty means imperfect models. That is what we have been discussing in this lecture. Like, we are simplifying assumptions, we are making wrong assumptions, we are doing underfitting, limited capacity, wrong structure. So all these leads to imperfect model. Now it is making sense to you that, okay, when I talk about imperfect model, what I am doing is that I am making wrong assumptions while building the model, while, or the structure I am using might be wrong, or the technique might be totally wrong, or limited capacity. The model might need more layers or more computing power, and I am utilizing like limited capacity. So all these factors will lead to model uncertainty. So too few layers, incorrect architecture. Now it's very clear that both of them, they interact. They interact means uh, uncertainty in the data will affect the performance of the model. The model, like, the performance of the model will be poor. And like uncertain data and perfect model, still we will end up getting wrong answers. Perfect data and uncertain, like imperfect model, perfect data, imperfect model, will end up getting wrong answer. So both of them are important. If we look at a real example, speech recognition. So let us suppose you get noisy audio. So the audio has got lots of noise. So because of that, data uncertainty will be there. Noisy audio, because noise in the data means data uncertainty. So in speech recognition, data uncertainty is noisy audio, and in speech recognition, model uncertainty is shallow model. So either you are using a noisy audio or a shallow model, both will end up giving you wrong answers. So fixing only one is insufficient. So the moral of the story is that whenever we are building the machine learning model, we have to be very careful that data has to be very proper, clean data. We have to eliminate uncertainty in the data to a very great extent. It might be that we might not be able to eliminate all the uncertainty, but to a very great extent, we have to eliminate the uncertainty in the data, the training data. And also, we have to put efforts in making models perfect. Like whatever assumptions we are making, like while deciding the features, we have to be very careful. Wrong assumption will introduce bias, underfitting, overfitting. That is very important. Limited capacity, wrong structure. So we have to be very careful. And when we like take into consideration both the clean data and the perfect model, then we will definitely get good results. The performance of the model will be very good. And still, the model is wrong because the output it will be giving will be approximate. And then we have to devise a mechanism wherein we can do the risk management, wherein if the model, like the you built a machine learning model with very good data and perfect model, you trained it. Now the next thing is risk management. What if it is giving wrong prediction? It should not, the risk should be managed, especially in the healthcare sector or in fintech sector. In healthcare, if based on the AI, if any decision is made, what if the AI made a mistake, then it can cause life, or in fintech it can cause losses. So diagnosing the source matters more than increasing accuracy. So now it's very clear that if you want to optimize the performance of the model, you diagnose the source, like the data, the model itself. Okay, now we'll look at why better data does not fix bad models. So it makes sense. Like let us suppose if we are using bad models. So bad models means it is having bias. It is either underfitting or overfitting. That's a bad model. Imperfect model. Now I think it's very clear what is imperfect model. Whether it is underfitting, like few features it is taking into consideration, or overfitting, it is taking unnecessary features into consideration. So that's a bad model. Some architecture you are using to build model is completely wrong. That's a bad model, imperfect model. So imperfect model can never represent reality. It has wrong assumptions. It might have high bias, high variance. So it is very like clear to understand that okay, regardless of very good data you supply to an imperfect model, the result will always be very bad. So more data just reinforces the wrong structure and you will end up getting wrong results. So let us look at one ML specific example, linear model on circular data. So this is something interesting. Now let us suppose the model is linear, but the data is circular. So model will not be able to learn. Now the data is very perfect, like the circular data you see now, it's awesome. But since the model is bad, because it will never be able to learn this circular data. So linear model cannot fit a circular data, no matter how much data you add. This is also interesting because here very big myth we are busting. It's a myth that okay, I am using 1000 sample size. I am getting a bad accuracy. Let me get 10,000 sample size. Let me get millions of sample size. And you will just end up wasting money in collecting the sample size because here the problem is not with the training data. Training data is absolutely fine. With 1000 samples, also, you can achieve some sort of good accuracy if the model is correct. If you can like here, instead of using a linear model, if you have used a circular model, then definitely you might have achieved a good accuracy using 1000 data itself, 1000 sample size itself. So now this is making very like a good sense to you that okay, this example is giving you a perfect overview. It's a proof that just blindly increasing the training size is not enough. It is not enough. Model also plays a role. So the ML insight which we can take away from this discussion is that data cannot teach what the model cannot express. If the model is wrong, data cannot teach. Okay, now we'll jump into the next topic of this lecture. Why better models don't fix bad data. Okay, this is also very interesting discussion we will be making. So even perfect models fail. So this is also interesting that okay, you made a perfect model, but if labels are wrong, if there is a uncertainty in the training data, if labels are wrong, inputs are corrupted, important variables are missing, then what will happen is that model will like end up learning wrong. Wrong labels means wrong patterns it is learning. So perfect model means model is capable of learning, but if you're feeding it wrong information, then it will end up learning wrong. So bad data is also like very dangerous. Important variables are missing. For example, like in predicting the house price, one very important variable is the uh, dimension of the house. Now, out of 1000 samples, only like 100 entries we have, and 900 entries are missing for area of the house in the historic data, historic sales data. Then our model will just like it will not be able to learn properly. So data makes sense when the model is perfect, and perfect model will make sense when the data is perfect. So both are important. So if we look at a ML specific example, image model with mislabeled data. So definitely model is very good, but if the training data contains 20% wrong labels, then the perfect model will end up learning wrong, and it will start giving wrong answers. So the insight which we can take from this discussion is that model power amplifies data flaws. So now perfect model means model is very powerful, but unfortunately it will amplify the flaws in the data. If the data high uncertainty is there in the data, the model will just amplify it. Okay, now we'll look into the next topic of this lecture, that is interaction between model capacity and uncertainty. So the idea is to balance bias and variance in machine learning, because we already saw in one of the slides that underfitting will lead to biasness, and overfitting will lead to variance. So high biasness and high variance both are dangerous. So if the capacity of the model is low capacity means the model is simple, underfitting. So low capacity means it is taking consideration into only into few features. There are many features which might influence the target. They're completely missing it. So low capacity will introduce bias. So low capacity will bias underfit, and that is bad. And high capacity means it is learning noise, unnecessary things it is learning. So high capacity will introduce variance. So overfitting. So the idea is that we should always look into optimal capacity. There's a trade-off. We should balance between the biasness and variance. So optimal capacity. So signal capture and noise resistance. So if we look at the ML specific example to understand it more clearly, neural network depth. So if the neural network is shallow, then it will underfit. If it is very deep net, it will overfit on small data. And if it is a balanced net, then it will fit well. So the moral of the story is that capacity reshapes uncertainty. It does not erase it. So the capacity cannot erase uncertainty. Uncertainty will be there, but it can reshape uncertainty. So I'll explain. It's a very interesting insight. See, no matter what you do, uncertainty you cannot remove, but capacity can reshape uncertainty. I'll give you a very interesting example for that. Let us suppose, okay, I'm just making a rough diagram. So these are like actual points, real data points. And if I'm using a linear model, then definitely I'm underfitting because I am just so all these things are the error. The distance of the blue points from the brown line is the error. Now with capacity, because here it is like underfitting. Now if I consider more features, I might like get something like this. Now because of that, see error I reduce, because if you look at this brown curve, the distance of that from blue points, many blue points to very less distance. So error I reduced. So that's why capacity reshapes uncertainty. I reshaped the uncertainty because error I reduced. Uh, so capacity can reshape uncertainty, but it cannot erase it because still there will be error. Like here, error is there. Still, error will be there. Okay, now we'll look into the next topic of this lecture, that is diagnosing uncertainty. So this is like the very important discussion. So as a machine learning practitioner, stop asking questions like why is accuracy low. So just don't look at the accuracy. Rather, you look into the entire process. So you should start asking like, is this data uncertain? Like whether there is some uncertainty in the data. So as a machine learning practitioner, you should ensure that the data should be properly pre-processed. It should be very clean, and we should eliminate uncertainty to a large extent in the data itself. That's the starting point, like a very important point. Then you should aim for perfect models. You should eliminate uncertainty from the model. And then you should also look into the coverage. Coverage means like the assumptions you are making, like the features you are considering. There might be many features which might be influencing the target and you are not looking into it. Coverage will also mean the sample size. It might be that model might need more patterns to learn. So the size of the training size. So now it's very clear. So that is what is we call as diagnosing uncertainty. So you have to diagnose uncertainty and not the accuracy, because most of the developers, machine learning practitioners, they make this mistake. They end up diagnosing accuracy and they get puzzled what to do. So instead of straight away looking into accuracy, you start diagnosing every phase, like data uncertainty, you diagnose model uncertainty, Then you diagnose coverage uncertainty. And if you do that, then correct diagnosis will lead to better decisions, safer systems, and faster improvement. Ultimately, you will end up getting high accuracy. Accuracy will automatically increase if you do this. So, better decisions, better, safer systems, and faster improvements you will achieve. So, finally, we completed this lecture. So, in this lecture, we saw that okay, models are approximations, they are not reality. Reality is something like it is infinite data, it's very complex, but the models are approximations. Model bias creates unavoidable uncertainty. Underfitting and overfitting, they reflect different types of failures. Data uncertainty and model uncertainty both are different. Now I think you got a feel of what do you mean by imperfect model, like model with either high biasness or high variance, like underfitting, overfitting. So that will lead to imperfect models. And there is a difference between data uncertainty and model uncertainty, and both are important. Yeah, and we saw very important thing that rather than focusing on accuracy, if we focus on diagnosing uncertainty, ultimately accuracy will improve. So I hope you got a very good understanding from this lecture. You enjoyed this lecture. So do subscribe to our YouTube channel Scale Up University for more such interesting lectures and courses. Thanks for watching. Thanks for your time.